Thank you all. Thank you, Ganga, for inviting me and for giving me an opportunity to discuss some work I've been at for a few years now. This is a symposium on soft and living matter. This, I guess, diverges a little bit from the first few talks that of the scale of the problem. We're all soft. We can feel ourselves, and we're all living. So, I took the liberty of adding this as my topic for the talk. Let me start by acknowledging most of what you'll see is Ahmed's PhD work and Ajinkya's master's work. My collaborators Pallab and Sumesh, my colleagues at IIT Madras. Alessandro is another collaborator from TU Eindhoven and Mike from ULICH. I first sort of came across a man named Mahadevan when I got interested in understanding falling leaves. I was trying to do some experiments in my lab. And one thought led to another, and I asked, how would a Mobius strip fall in a tank of water? And I had everything set up, and I was getting ready to do the experiments. And when I said, is there any paper out there on the fluid dynamics of Mobius strip? It turned out there was. And so I pulled this out, read the paper, and sort of replicated it. I presume this was your PhD work. It was done in the Department of Mathematics at Stanford. And the part that trips me even today is that the resulting shape is shown to agree well with a band made from a strip of plastic, all being in a mathematics department. So that shows, who Maha was, I guess, as a young graduate student. Another lesson to all of our young friends that it's always a good idea to bear an experiment that whether you will end up doing it or not, bear the experiment in mind. So I'm going to talk about crowds, and I want to tell you one of the highest privileges I've had in being in this field for some time now is we were part of a small team that got invited to the Mahakumbh in 2025 to sort of oversee their crowd management system. And I must start by telling you, this was a phenomenally well managed, in spite of everything that we see. We hear, I mean, as an event of this scale with both US and Canada converging on one city is simply unimaginable for everyone outside. But I had the absolute honor and privilege of being there for some duration of time, watching crowds, as it turns out, and learning, how people behave. I want you all to imagine what this crowd would have felt like from just that one number. On the highest day, on the Mauni Amavasya day, the crowds right near the bathing ghats were upwards of 9 per square meter, packed over a 200 meter by 200 meter bathing area. So you can imagine this is as close to continuum mechanics as one gets. I'll show you some videos in a little bit. This is another sort of temple festival that we got invited to, that we consulted with the police to arrange. This is a town called Pandharpur, where on this Ashad Ekadashi day, roughly about 1 million people walk through that town. Only a very tiny fraction actually go into the Vithala temple to have darshan, but they just want to come to the town, be there. And you can see, this is basically a quad flow with both the walls being driven. You will see this. I couldn't speed this up because this is a drone shot and it's very hard to follow the features if I sped this up to make it more interesting. There is a stream of people going this way, another stream coming this way, and you see these police people in the middle. They are in the highest shear zone of this driven flow. Okay, and it gives you a sense of what police go through when you watch this. You can see how orderly the crowd is. This, just to give you a feel, is at the level of about 6 to 7 per square meter density. Now, this is the tawaf of the Kaaba. This I have been able to speed up 10x because this was from a stationary camera. You can see a nice lid-driven cavity. Again, if I didn't tell you these were people, you would just believe this is a multi-phase fluid dynamics, very simple multi-phase fluid dynamics lid-driven flow problem. But the beauty of this lid-driven cavity is it's a Stokes flow at the continuum scale, but compressible. You can, if you pay a close attention to the wave, to the field here, to the velocity fields here, you can actually pick up compressibility waves. So this is like a continuum mechanician's delight that you can actually do experiments on compressible Stokes flow, if there is such a flow out there. Okay, these are all once a year ideas, but this is an everyday occurrence in Delhi.
Why do you call it a Stokes flow?
Because on the scale of on the scale of the sort of the viscosity and the mean velocity, the Reynolds number of this whole continuum, so to say, would be very, very small. I'll show you some ideas. I mean, the answer is very tough, but difficult, but you'll have to put people in a viscometer and shear them, right? Effectively that. But yes, the answer is that. Now, this is a daily occurrence in the Rajiv Gandhi metro. You see people come out and there are people waiting to board. Anybody that has done intermediate fluid dynamics class would spot an inflection point in the velocity profile. That's never good, right? So this is an inherently unstable flow field. And this is what happens every day in metro stations all over the world. Okay, now there are two kinds of bad things that happen when crowds of this scale assemble. There are these things called stampedes and crushes. Just want to distinguish the two. Stampede is where people are running helter-skelter and you're actually, in a very unfortunate sense, stamping on somebody else, and that causes loss of life. Crush is where people are just standing upright, where they are standing. You can imagine, I've actually seen pictures and videos. You can spot hexagonally close-packed arrangements when you get to this 9 per square meter kind of densities. And so people are just standing where they are standing, and it's an active fluid effectively. Now, when you have these density waves result in pressure spikes, and these pressure spikes end up asphyxiating people. So crush is actually a far more devastating occurrence than this idea that people run helter-skelter and stamp on each other. There was, previous sort of occurrences of crush. The last one in Mecca, after which they completely redesigned the tunnel, was one of the most devastating crush instances that has been recorded. This is a picture of the love parade in Duisburg, and which resulted in a crush. But again, you can see there are walls, and this is an enclosed space, and the density waves that propagate back and forth are essentially the result of are what caused the fatalities. So let's see what is it that we want to do now that we've sort of laid the foundation for how dense crowds behave experimentally. We want to see if we can develop a computer model, and we will go after an agent-based model in a little bit, to understand motions, to understand how people move, and see if we are able to do some real, I'll say, controlled in a very loose manner experiments that we can use to understand how these models are sort of become grounded in reality. So I'll spend some time on this. So the core idea is you write an evolution of the velocity of a given agent subject to three separate forces. The first one is a soft sphere repulsion force. Every person wants their little elbow room as much as they can. Second is a self-propelling force. I have a desire to walk in a particular direction. The desire could be, the self-propulsion could be driven by one of two possibilities. One possibility where I'm walking along my current instantaneous velocity vector. And that's all I can do because there is a crowd around me. A second is where I have a motive. Let's say I see an exit, I want to go towards an exit. We'll see some results of a motivated agent a little later, but this is an unmotivated, self-propelled individual. A third is a drag force, loosely called drag again, which results from with my current velocity sort of not being coordinated perfectly with my immediate neighbors. So there's a penalty associated with me not being coordinated with the average velocity in some weighted sense of my immediate neighbors. So these are the three forces. And you can see that for very low coordination, this mu that you see here is arising out of this lack or presence of coordination. So at some value mu, you'll see that these agents are rather uncoordinated and you'll see a disordered phase at the bulk scale. Once this coordination increases beyond a certain critical point, and I'll show you where that arises, you'd start to get some organized motion. Now here you can see the density waves a little more clearly because this is a cleaner simulation. Uh, the colors are just for better visualization. If everything was just blue or orange, you couldn't tell these features. So one could imagine, I mean, we just put a bunch of oranges in the middle, leave the blues on the periphery, just to sort of see what they are happening, but they're all identical agents. So very low value results in near thermal-like motion, and a higher coordination coefficient leads to this collective motion. So there's a self-repulsion, particle. So this is just a soft sphere self-repulsion. Yeah. Yeah. So that's exact. Thank you for pointing that out. The old Vichek model, which is the grandfather of all of the models in this field, essentially is a non-inertial version of something like this. So the idea of adding inertia at the agent level basically allows for noise to originate intrinsically. So the agent, when they sort of are up against another fellow agent, they have a decision to make whether to go right or left because they have an inertia. And that automatically induces noise into the system, unlike the old Vichek model. Well, you can draw a certain radius, a cutoff radius, and we count, it's a linked list essentially. You keep track of all of the neighbors in a given cutoff radius, and you do a weighted average of those neighbors. You would have to assume that this fellow a little bit farther away is propagating his presence and information thereof through these layers. And well, the answer is this. The weightage sort of drops off exponentially as you go farther and farther away radially outward. We have not modeled vision. So in other words, there is a cone in which I'm able to see. But let me tell you one thing. I've actually seen crowds at this 9 per square meter. You can just keep your eyes shut. There is no use of vision, or there is no use of even your own all of the muscular energy that you may have. You're just going with the flow. Huh? Not if? Everyone. Well, yeah. I mean, my basic point is that at this scale of 8 or 9 per square meter, your own agency is quite a bit suppressed, other than the idea of walking with the crowd and walking in your own velocity, in instantaneous velocity vector direction. Even to do that. Correct, you're right. If that's all you have agency of. And this 7, 8, or 9 per square meter occur in almost all of the examples I showed you in just a little bit. So whatever is the instantaneous velocity vector of the particle. So it's obviously I'm basically allowed to exert a force or accelerate in the direction of my instantaneous velocity vector. That's this model. We'll see what happens when we add motive in a little bit. Okay, so the order parameter we chose to sort of distinguish this transition is essentially a radial speed, essentially like a time averaged, ensemble averaged speed on the scale of the whole collection of agents, which would be nearly zero in the disordered state, and you would show a finite speed of motion in the ordered state. What we show here is that order parameter as a function of this coordination coefficient. Initially, for very low values of mu, the field is disordered, and there is a sudden jump to an ordered state at a critical value. And then when you reverse it, you see classical hysteresis. We were able to show that this is truly a first order phase transition. And also that if I was to try to control this process and bring it back from from disorder back to order, the optimal placement of, let's say, police personnel would be in the region where the velocity is a maximum or shear is minimum. So essentially, wherever, if you were to plot the mean velocity profile, it would increase and then decrease again towards the wall. So where that velocity reaches a maximum, we showed was the sort of the optimal location for energy injection to control the crowd. Yes. So beyond a certain critical value of density, we can show that, well, these two numbers would be functions of density. Yes, the answer is yes. Correct. So I'll show you some examples. Correct, you're right. These are all, this would be true when you are in that really densely packed state. Yes, Srikanth. The first set of simulations, I'll show you some others a little later, but this was a simpler experiment, simpler computational experiment to go after. That's the reason we did this.
You don't do anything with how to interact.
No, the confinement is just a bunch of stationary agents.
The order parameter you're choosing doesn't really tell you, it tells you that there is a net velocity.
Correct.
You don't know long term how that.
No, we were trying to identify this phase transition. You're right. So now we ask the question: is there these abrupt phase transitions from order to disorder, particularly, is never good, right? Because you don't know, a certain lack of coordination between neighboring agents suddenly results in disorder. So we wanted to see if there was a way to avoid these sorts of abrupt transitions. Before I get to that question, I just want to show you this particular video where you can see one of the intermediate states just prior to transition. This is a gel. So you can see going from what looks like near thermal motion to a gel to orderly state. So there is the process of that first order phase transition seems to show all of the sort of the necessary signs. Now we add a motive to say, I know a certain direction that is pointing me to the exit. Yeah, Maha. It seems to go through that phase. Exactly. That middle phase is the jammed, what I call gel, but it's like a solid hexagonally close packed state. Correct. Correct. We've sort of quantified that, and the answer is yes. Exactly like Srikanth would find in a granular, in a jammed state. Correct. Sure.
I think it's well, with the key differences, it looks like a fluid identity. There's a net velocity is different.
So we add a second sort of motive for the agent. Not only am I now allowed to move along my instantaneous velocity direction, I know a certain direction I want to take strides towards. And when we do that, essentially one can imagine this gamma divided by a beta as a dimensionless parameter that quantifies the competition between my motive to get to the exit and my instantaneous motion. Gamma equal to 0 gives you this same hysteresis. These are for two different values of beta, meaning two different sort of intrinsic motivations to move in the first place. But what we find is that as gamma increases, this hysteresis completely disappears. Meaning, if you show, in simple lay terms, if you show a large crowd a motive, say an exit or something to do, this hysteresis and sudden transitions associated with that hysteritic phase transition seem to be suppressed. So now we ask the question, what exactly is the nature of the transition as I change gamma? When I go from gamma equal to 0 upwards at the same value of mu. This direction is what is governed by the disordered phase going into a hysteresis zone to the ordered phase. If I move along one of these vertical lines, what we show is that at this critical value of gamma, there is a second order phase transition. It's a smoother phase transition. It doesn't show the characteristics of this first order jump, so to say, but it's a smoother phase transition, but nevertheless goes from disordered to ordered phase. I can show you. So this first video, what you're showing is increasing gamma at a particular mu. You can see that it goes from essentially what looks like thermal motion to, as gamma is continually increased, it goes into this state where there is some orderly motion that appears. In this case, we've chosen to sort of, the gamma is basically in the direction of the radial, of E theta, basically. So the motivation that the individual here has is to just go around like a cleaner circle. You could do this with, pointing to a certain exit, and the agents would sort of move towards it in a little bit more of an orderly fashion than if you were to just let them move in the current velocity vector in a direction and discover that exit all by themselves. So you can now sort of scan the parameter space, this beta, mu, gamma, and sort of show the complete picture that there is a region in the beta gamma space where one would observe disordered crowd. And for every given beta, which is my ability to walk, there is a critical value of gamma that would give me ordered motion. I don't have it in these slides, but it's actually in the supplemental material of one of the papers there. Yes. Okay, so now, yeah. Non-centrality. Correct. The beta times instantaneous velocity vector. That's determined by the motion itself. Okay. So then we said, what's the best experiment we could do? Yes, sir. Yes. Crushes are actually more common in the ordered state because you get these very so one of the work we did with the Pandharpur police was when these pilgrims bathe in the river and they're all coming back. Imagine the river bank is like packed at this level of 8 to 9 per square meter. And there is a watchtower, and I had the pleasure of going up there to see what this crowd looks like. You can see density waves, going several hundred meters, swaying back and forth. And they were asking, how do I now minimize the chance of crush? So we gave a very simple fluid dynamic suggestion to break up the whole crowd using stainless steel barriers. So the compartments in which these waves are contained is smaller than the bigger length scale. They did implement it. So the idea that crush can occur even in an ordered flow, and how do you then mitigate the effects of such a crush by essentially breaking down the length scale? Yes, sir. Of that, that's coming from the compressibility of the individuals in the. It's exactly like any other Mach wave. There is a compressibility of us individuals, and that determines the.
So these are sort of waves in a linear regime.
They seem, I've not studied those waves other than the fact that.
The simple sort of vibration like.
They seem very much like a linear vibration, except if you have a wall. If you have a wall and this is an active material in the middle, right? So if I am trying to, as we all know, a standing individual is unstable, right? So if somebody pushes me, I'm trying to actively control my position, my attitude in some way. If that activity is now adding, and if it adds energy to this traveling wave back and forth, my intent to control myself may actually come back to hurt me. Sure. So I'll quickly show you some experiments we did at Chennai Central. We took one of the platforms in which there's a regular metro train that comes, individuals evacuating. Then we ask, if I want to make sure this train is evacuated as quickly as possible. Now remember, these are sparse crowds. These are nowhere near the densities we saw. But it's hard to do experiments in any higher densities than this, controlled experiments at least. So we wanted to see if there was a way to nudge this crowd to walk along the shortest path and not be distracted by this additional route. So you start by placing your cameras, you talk to the Southern Railway, get their permission, then you get the Institute Ethics Committee approvals. So we went through all that and then set up our cameras in Chennai Central. You do a perspective correction to make sure your trajectories are real. And then you use a standard tool, like there are a couple of tools in this field, one called P-Track, and YOLO, of course, is an all-pervasive computer vision tool. You're able to track the head separately and the feet separately. So you are able to quite accurately locate the center of the center between the 2 feet. And that gives us a sense of a trajectory of a given individual. Now we tried 4 different kinds of interventions. Start here, just put some passive cones and let people decipher. Second, there's a sign that says go this way. Third, there's an active steward. And fourth, of course, our nuclear option, a police person, right? Now, I want to take a quick poll as to which ones you think worked. The passive one worked. Well, we are not yet that utopian. This is the baseline trajectories going left and right before the intervention. And this is with the police person, where roughly half and half, went on either side. With the police person, upwards of 92% went the way the policeman pointed out. Okay. Another way to quantify this is to look at the residence time of the individual. So you plot a residence time distribution of a given individual. The maroon line here is the baseline, and you can see police, steward, signboard, obstacle, they're all left shifted, which means people are actually evacuating faster with all of them. So it turns out when you do a little statistical test, all of them are significant, meaning they did do their thing, but the police was, of course, significantly more effective. So this gives me a lot of hope for India in the future, that we're not as bad at following signboards. Okay, last point I want to make is there is a way to get to the crowd density and crowd pressure from this sort of video. So you can do a Voronoi tessellation of the sort of the space around an individual and calculate exactly what the densities are. This red fellow here is under some duress, as you can see. So you can now go back and look at a video of how this evolves, and that will give you a picture of a little more of a dynamical picture of what's happening with these individuals when you look at the tessellated region around each individual. This is still very sparse, but the problem with doing something like this in the dense crowd is aliasing in the computer imaging. It's extremely difficult. You can't hire enough workforce to click on heads after heads after heads to sort of identify them uniquely. But I guess this gives you a picture of how one could go about. In fact, we did one more. We can look at the fluctuating component of the velocity at any given point and estimate the granular pressure, which is the pressure on that individual, and sort of see what could be done. So just a little sidebar here is the first fellow that takes a track is very much, we have, I don't know where we have our own pheromones, but we have a pheromone trail of our own as humans. So I'll stop here. Managing high density crowds with existing infrastructures is challenging. We believe that having a model-based approach to managing crowds is a starting point. We made a small trial in Pandharpur, and we showed the sort of the reduction in the crowd pressure, and it's a good thing to sort of experience, that you do some simulations, you go tell the police, they go do a trial, and it seems to sort of give some good results. For those that are, for our students and young friends in the audience, I'll say one last thing, that however rich of a theoretician you may be, have one very early conversation with an absolute end user. Whoever would be the absolute end user, end beneficiary of the work you are about to embark on, have a conversation with that person. I'm not suggesting you should jump into becoming translational scientists, but having that first conversation is very important. And it has helped us in this direction as well. Okay, thank you all.
Thank you, Mahesh. Questions?
Yes, so that's exactly how good crowd management systems work. They are one of the recommendations for Pandharpur was to actually control the average crowd density, right? So you control the average crowd density by controlling inflow and balancing it instantaneously or in a time delayed sense with the outflow. So that's how police actually manage crowds. They shut so they make it difficult for you to get to where you need to go. That's effectively what good crowd management looks like, right? So the answer is yes. Yes, sir.
This number, like 100 million people bathing in one day, seems difficult because you have to say that each person spends, let's say, 2 minutes inside the water and how many people are in the water at one time and so on and so forth. Have you worried about that question?
Not as a physicist or an engineer, but practically, yes. So you should see the mindset of the people that come there. They just want to be there on that day. They may barely get to the water. They may touch the water and sprinkle and go away. That's okay for them. Many people may not even get that far because there is no structured way by which there's no single inlet, single outlet into and out of the water. People are going in and coming out. So it's like I don't know if there is a physics analogy. It's like counter diffusing, two species counter diffusing. That's effectively what it looks like on the river bank. So most of the people know they will not be able to do the things they would regularly do if they went to Pandharpur. So it's unlike Tirupati. Tirupati is obviously a very, very structured crowd management system, single inlet, single outlet, and they know exactly what everybody wants to do there. Whereas most of these one-time or once-a-year festivals are not designed for something like, they don't have the infrastructure for that. No, well, Pandharpur, I've seen these days, all of the police have these so-called AI-enabled cameras that do head count, instantaneous head count in a given frame. They're not recording the whole image because that's just too memory intensive, but they are recording head count at 15 frames a second or 15 hertz sort of a. So they have data on the sort of the crowd density within the frame of view. And from that, they're able to estimate the overall crowd flow. It's like a Lagrangian, you are sampling Eulerian, but you want to sort of get the Lagrangian integral out of it.
Hi.
So in some cases, it may be exaggerated, but the order of magnitude is still okay, sir. I believe whether it's 1 million or 600,000, the order of magnitude is several 100,000 for sure.
Hi. Just to know, like for the Chennai suburban, which language did you put the signboard?
Which language?
Yeah, because signboard. Signboard, which language did you put the signboard?
Signboard was just an arrow.
Oh, it was just an arrow. Okay.
That arrow there was just an arrow that said, go this way.
Oh, okay.
And even that made some difference. You know, as users of statistics, we're not supposed to you're not supposed to use the absolute value of that P. You're only checking whether it is more or less than a certain confidence value, right? But if you go overboard, you can see that the signboard actually made a reasonable difference to
the overall. One more thing is, so you were talking about the confinement on the peripheral confinement. So if you see the Shabarimala, that I think that is Pulmedu tragedy. So that where the bottom topography made a impact rather than horizontal confinement. So how do you incorporate such thing?
Look, we have a model. So we'll have to look at what the sort of the dynamics would locally look like. right? So if there is a topology and people are climbing, I mean, I've not thought about it, and I don't want to give you an answer just standing on my feet. You know, I want to be able to do some work on it.
Yeah.
Yeah.
Thanks.
But if you put these kind of defects, does that cause a change in shape?
Yes. So there are experiments on sheep where they show that actually inducing a defect increases the throughput of sheep. So for example, if I want to have sheep exit out of a certain gate, like imagine the gate is 3 sheep wide or 2 sheep wide, 2 sheep wide. If I put a little round tana some distance away, by streamlining the flow of sheep towards exit, you actually decrease the evacuation time of that sheep. Correct. So you actually adding certain clever defects would actually, aid or not thought about it, but if it is altering the overall dynamics, it may also have a.
Do you have data from the pedestrians either leaving trains and or in one of these confined zones to look at how fluctuations decrease? So you're talking mostly about a hydrodynamic picture, but if I think about not just the mean, but the fluctuations in the velocity, do the fluctuations start to go down as the density starts to increase?
Yes.
And do you start seeing slug-like motion rather than individual motion?
So I had one undergrad student do some basic analysis on one of our videos. You can see some initial signs. I don't want to go overboard and claim. You can see some initial signs of turbulence lamina or like a re-laminarization transition. So one can look at, I'm happy to have this discussion offline, but there are some parallels to laminar turbulent transition in the order disorder transition as well.
But if I just look at the individual coefficient of variation, it starts to decrease as the density starts.
As the density increases, yes. Because that as the density increases for the same mu, your coordination is increased. And so essentially like you are more gooey fluid at the continuum scale. Right?
Take one last question. Yeah.
Sir, you mentioned the optimal placement of policemen to control crowd is at sites of maximum velocity and minimum shear.
Minimum shear, correct.
Why is that the case? Why
So,
minimum shear?
Again, our initial simulations showed that at those positions, you are able to sort of optimally remove the fluctuating component of the energy. So like Maha just said, you have the energy in the mean flow, and it's the fluctuation that I'm worried about to sort of, if I can remove energy from the fluctuating phase, then I'm able to sort of calm the whole transition down. So that's, I mean, we've not done much work in like the causal nature of that, but that seems to be a direction that. So in these configurations, the maximum shear is very near the wall, right? So in fact, we've done these experiments in another single inlet, single output, single outlet. So imagine a single inlet and I don't want to.
No, please go ahead. Right.
You're okay. All right. So if I have a single inlet and a single outlet, you have essentially what looks like a jet stream and 2 trapped vortices. It turns out that the optimal placement even there is where you have the least velocity fluctuation.
Yeah,
Just a quick, there's a nice paper by Bartolo on crowds in Pamplona, where he measures density fluctuations.
Okay.
It's a very nice paper.
I will. Sure. Thank you.
So I'm sure that there are more questions, but we'll take it to the next session. So let's thank Professor Mahesh for this nice talk.